Let's start. Hi, everybody. Hello. My name is Hagay. I'm an engineering manager with Amazon AI, based in Palo Alto, California. And I'd like to talk to you today about model serving for deep learning, although most of my talk can be generalized for just regular machine learning. Yeah, just a bit about myself and what I do. As I said, I'm an engineering manager with Amazon AI. Most of my focus is spent around deep learning systems and tools, frameworks like MXNet, Onyx, and in general, tools that allow developers and engineers both inside of Amazon and outside of Amazon, including AWS customers, to use deep learning, adopt it, and benefit from it for their business purposes. And my talk about model serving actually discusses just that. So let's get going. So I'll start by just spending just a bit of time to talk about deep learning and why it's a big deal. So if you just look inside Amazon, which is the company I work for, you can see how impactful deep learning is already today on both Amazon as a company and our customers. You look at the Amazon.com, the retail website, you see lots of personalization that are delivering a better user experience, personally tailored experience for our users. Lots of that today is powered by deep learning. You look at the fulfillment centers where all the logistical magic of Amazon happens. There are robots called Kiva robots inside these centers. Lots of the algorithms that are powering up these robots are actually powered by deep learning. You look at the voice revolution with the introduction of the Alexa device by Amazon. That's a device I'm sure you're familiar with. It's powered by natural language. Many of the algorithms used in Alexa are actually powered by deep learning. And lastly, Amazon doesn't yet has a self-driving car, not that I know of, but it does has an effort that was published already with autonomous drones to deliver packages. Lots of the vision tasks handled by these drones is handled by deep learning. So again, you can see the amount of impact deep learning has. But there's another reason why deep learning is a big deal, and that's also how well it does. This is an image of a cat, and under the image of the cat, you can see different classes. Now, this is a problem known as image classification. Given an image, identify the most prominent object in that image out of a set of potential classes. Usually, it's around 1,000 classes. And this actually was a pretty hard problem in computer vision until recently. Today, it's mostly considered a solved problem, thanks to deep learning. There was an annual competition called ImageNet competition, where different universities and research centers would submit their algorithm or model to compete in this competition. In 2012, Alex Krichevsky had submitted a new algorithm to solve the problem. That algorithm was based on a neural network model. It was called AlexNet. And that submission really marked, I think, the beginning of the deep learning revolution, because that model actually beat the best model to date by something like 30%. And this is a competition where incremental improvements were measured in fraction of percentages usually. And it was a new model that beat the best model to date by around 30%. So that was huge. Since that year, since 2012, every year, the winner of this competition was based on neural network. So that was, kind of as I said, the beginning of where deep learning kind of took over lots of machine vision, computer vision problems. And more explicitly, you can see that deep learning was doing better than other vision algorithms and other machine learning models. But then there's also how well this technique does compare to us humans. We were trained by millions of years of evolution to be able to handle these visual perception problems. So this graph that I extracted from a survey done in 2017 compared a few models, vision models, like AlexNet that I mentioned earlier, VGG and GoogleNet, compared to human participants. on a problem pretty similar to the image classification problem I mentioned earlier. As you can see the results here, that study found that these models, which today, by the way, are not state-of-the-art, are outperforming humans, or the average human, on these tasks. So that's another reason why deep learning is a big deal, because in a growing number of problems and tasks, it's able to do better than us humans. And you can take a step back and think about the impact this can have on how we can automate and improve the productivity of ourselves with this technique. So deep learning is a big deal because it's able to do better than us. So hopefully, now that you're convinced that deep learning is a big deal, the next thing you want to do is train a model and deploy it in production. And then this kind of raises the question, okay, so what does a deploy model look like? So on one hand, we have our model, which we took a lot of time to train. It took a lot of time to prepare the data, etc. But at the end of the day, we have a model we're happy with, and we want to use it. And on the other hand, we have a bunch of clients that want to be able to run prediction or inference on that model. It can be mobile clients, desktop, IoT, or other cloud services. What we really need to have a deployed model is some kind of a scalable server that exposes an endpoint over the internet, over the local network, so clients can call that endpoint. And on the other hand, it encapsulates that model for prediction. That's a pretty simple diagram. And by the way, it's not very different than what you would do if you would want to deploy a web application. But that's really the basics of it. That's what we want to achieve. But then there's a lot of what we in Amazon call undifferentiated heavy lifting that involves doing exactly that same thing that looks simple. And I'll go through just a quick list of that. First of all, we want that server to be performant, which is extremely important, especially when deep learning is involved, because deep learning is very intensive computationally. If you take a state-of-the-art neural network like ResNet 152, which has 152 layers, just one forward pass through that network takes a billion of floating point operations, just one inference. And imagine if your service has hundreds of concurrent users. This means hundreds of requests per second that needs to be handled, and each one of them means billions of floating point operations. So performance is extremely important. Availability, just like most other services, is extremely important, especially when you deploy a new version of your model. You don't want to take your endpoint down when you deploy. You want this to minimize the downtime, or ideally have no downtime at all. Networking is important because the interface to which you expose your model is based on networks. You want to support the standard protocols like HTTP. You want to do proper error handling, etc. If you ever owned, another point is if you ever owned a service in production, you probably know that you want at any given point in time to know exactly how your endpoint, how your service is doing, how many requests are coming in, how many errors are there, what's the latency. So you want to have good monitoring in place. You want to decouple your model from the underlying server service infrastructure because you might have different types of models. You might have a recommender system. You might have a convolutional model for vision task, an NLP model, etc. The server infrastructure should stay the same. It should be decoupled from the model itself. And last two aspects, which are kind of tied together, you want this to be cross-framework, because you might use different frameworks for your models, like MXNet, TensorFlow, PyTorch, or whatnot. And you also want this to be cross-platform, because sometimes you might want to run your server on CPUs, sometimes on GPUs. You want a server that is able to support that. So that's a lot of things to take care of. And that's what we call the undifferentiated heavy lifting. And I'm going to talk to you about the model server for MXNet. It's an open source project that we on Amazon AI have built. All of the code is open source. You can check it out. You can contribute. And I'll talk about how you can use that to achieve exactly all these things. First, I'll give you a brief background on Apache MXNet. So with a raise of hands, who has heard of Apache MXNet? Okay. Who has actually used it to build models? Okay. So it looks like you need some kind of a background on MXNet. MXNet is an Apache open source project. Apache is an organization that provides umbrella for different open source projects. One of the most well-known projects is the Apache web server, which at some point powered like 80% of the internet. And now, there are a lot of very interesting projects that are being run under this organization. One of them is Spark. MXNet is another one. It's a framework that allows you to build and train neural networks. So it's similar to other frameworks out there, like TensorFlow, PyTorch, CNTK. And it does a lot of things like automated differentiation for calculating the gradient and provides optimized layers. It really abstracts all the complexities around building neural networks. It was created by the academia, collaboration between CMU and University of Washington. And AWS actually adopted it late 2016 as the deep learning framework of choice because of two main reasons. One is the broad API support. So MXNet supports different languages that you can use beyond just Python. And the second one is the immense scalability and performance. MXNet scales extremely well, and there's lots of benchmark out there on the internet. You can look to see how it compares to other well-known frameworks. Some highlights about MXNet. So if you think about ease of use, MXNet provides both imperative and symbolic API. It provides API in a lot of different languages. Python, obviously, but there's also a Scala API, there is an R API, and there's a bunch of others. There's also toolkits for vision and NLP that really I recommend to check out if you're interested in these domains. Performance, as I said, is one of the sweet spots of MXNet. It has optimization for CPU, GPU. The distributed training is highly scalable, and it supports the advanced features like quantization and nickel. And it's portable. You can train on the cloud and then predict on edge. MXNet actually has a build for ARM devices that you can use. It has a model serving framework that I'm going to talk about now. And if you're a Keras user, then it also has a backend support for Keras. And then the model server, it's a server framework built on top of MXNet. It's a machine learning model server that serves both MXNet and Onyx models. It automatically sets up HTTP endpoints for you. It auto-scales to all of the available CPUs and GPUs you have on your host. It has pre-built containers that are optimized. And it has a command line interface to package model artifacts for serving. And lastly, it's an open source project, so you can check out the code, you can contribute, you can file issues, and communicate directly with the developers working on it. So now I think it's a good time actually to show you guys a quick demo to show you a basic use case of the model server. So I pre-recorded it. So to install it, it's very easy. You just do a pip install MXNet model server. And model server will install all of the dependencies, including MXNet, and will set up everything within just a couple of minutes. So that's it. Now the model server is installed. Now let's take the next step. Let's do a quick pip show command to make sure that it's installed. This demo shows a pretty old version. The latest version is 0.4, and version 1.0 is coming out real soon, and I'll talk to you a bit about that, what it includes. So now to use the model server, it's very easy. MXNet model server -h shows you the command line arguments you can use. So there's a bunch of them here, but really the important one is -- models, which you can see here, which allows you to provide key value pairs. You can provide more than one for the model you want to host. So the key is just a key name for the model, and value can be a pointer to a model, either on the local file system or even over a URL. And let's see how this looks like. So now I want to host and serve a model. First of all, just for this demo, I will go to the GitHub repository of the model server, where there's a lot of documentation that is available, and also, of course, the source code. But that's a great place to start if you want to learn more about the model server. But where we'll go here now is under the docs directory, there is a model zoo README, which includes lots of models that are pre-trained. You can just use them for inference. So lots of vision models, but there's also some other models there. In this demo, I will just take SqueezeNet, which is an image classification model designed for mobile devices, so it's very compact in size. That's why I chose it for this demo. And on the model zoo, there are a full example of how you would use it. So let's just go and just copy the link to the model file. So this is just a URL. And I will see how we can use that URL. So we'll do an MXNet model server, -- models. We'll give it the key name SqueezeNet and the URL, and just hit enter. Model server will now fetch this model, download it locally, unpack it, load it into memory, bind it into MXNet, and be ready to serve it. And you can see that now model server is running on localhost, port 8080, which is the default, waiting for prediction requests to come in. And now let's go ahead and do a prediction request. So this is an image classification model, so we should provide an image as the input for the prediction. First, we'll ping an endpoint called the ping to check that the server is running and the endpoint is set up, and we can see the response is a JSON saying, hey, the server is healthy and running. Now let's go and just grab an image, and as is custom in deep learning demos, we'll take an image of a cat. So we'll do a curl-o to download that image of the cat locally. And now let's go and just do a prediction request. Oh, first we'll make sure this is a cat. Okay, it's indeed a cat. Now for a prediction, again, we'll use a curl command, which just generates a HTTP post request. We'll send this request to localhost where our server is running, port 8080. And notice the endpoint is SqueezeNet, which is the model name we provided, /predict. And then what we do, we provide a binary JPEG file as an attachment to the request. So that's a file we just downloaded. And just hit enter, and boom, we can see that we got a prediction. The server processed the image, provided a prediction, and that's the top 5 classes. And you can see that the top 1 is Egyptian cat, and I have no idea what is an Egyptian cat, but I trust the model. Okay, cool. So now that we've seen the model server in action, let's briefly talk about a few key features of the model server, and we'll start with the model archive. If you recall, when we provided a model over URL to the model server to load into memory and to start serving, it was actually a file, a single file that has the suffix .model, and that's what we call a model archive, and let's talk about what it actually includes. So first of all, it contains the trained neural network, right? That is, of course, essential for serving the model, and that's the basic thing. That's what takes most of the memory, and more specifically, the parameters of the model. But then there are other things. There is the model signature file, which basically tells the model server what's the input it should handle for both the network endpoint and also for the model itself. And in this case, in the case of the demo, the signature basically asked the server to accept JPEG images as inputs, and then it also told the server, hey, and by the way, the input shape for my neural network is with these dimensions, and then while the server is smart enough to understand that it needs to take the JPEG image, convert it into that tensor, and feed that tensor into the network for inference. So that's all detailed in the model signature, and I'll show you that in a minute. And then there's custom code. You know, in the real world, production services never just run the neural network. There's always things beyond it. There's pre-processing of the inputs. There's assertion for input data. There's some bifurcation in the business logic. And all of that should be part of your endpoint. And that's exactly why we have the custom code. It allows you to basically, it's an optional, by the way, thing to provide in the model archive, but it allows you as the developer, as the engineer behind the service, to add your custom logic before inference is done and after inference is done. And you can, by the way, also override inference itself if you want to. Now, that's a very useful feature, and I would say it's actually a must for every production service serving machine learning model. And lastly, you can include whatever other auxiliary files you would like that you will need in your model. And these auxiliary files are accessible by the custom code you're running, and you can use it for doing a lot of different things. It can include configurations. It can include scene set, which details the set of classes your classification model uses, and other things. Now, all of these files are basically exported through a model export command line interface, which is part of model server, into this one single file we call a model archive. And that model archive is handled by the model server. Let's do another quick demo and show you what this looks like using the model creating the model archive and using it. So in this local directory, you can see we have a bunch of files. Let's just go over these files. So the first one we'll open is the squeezenet symbol.json. That's an MXNet neural network file that basically details the neural network that we're running. And you can see that the first node has a name data, that's the input node. You can see a convolutional operator here. You can see the activation function, right? So it's nothing you need to worry about too much. MXNet generates this for you, but it is an important input. And this is the output of the softmax. The other thing that we have there, which is I spoke about, is the signature. So you can see here in the signature, you can see the set of inputs. You can see the input type, which is image JPEG, and you can see the outputs. All of that basically tells the model server what inputs to accept and what outputs to provide. Scene set, that's the set of the 1,000 ImageNet classes, and we provide that to the model server in the case of this model, so model server can actually attach the right class name. And lastly, the custom code. So in this case, it's the MXNet vision service.py. So this is Python code, as you can see. You can see the function preprocess that we're overriding. You can see post-process. And this Python code allows us basically to, just stop here for a minute, just briefly talking a bit more about the custom code. So this custom code, which is in Python, because usually we train our models in Python, so we find it most suitable to use Python for the custom processing, allows us to tell model server, hey, with every incoming request, please run this code before you start inference, and that's the code that is under the preprocess method, and please run the post-process after inference is completed, and this allows you to customize completely the entire request handling process. And this is optional, so if you want model server to just do everything out of the box, model server doesn't require you to provide the custom code. You can just not provide code. Model server will automatically take your inputs, convert them into tensors, and feed them into the network for inference. And we'll take the output, and we'll serialize the output into the JSON response from the server. Okay. And then to export all of that into a model archive, we just do MXNet model export. We provide the model name, we provide the path, and then hit enter, and that's it. We have our sn.model file generated. Okay. So after we understood the model archive, I want to talk to you about the endpoint that is generated. So the model server generates REST-like endpoints, model name / predict, like we've seen earlier. These endpoints are auto-generated from the model signature.json. It supports JSON encoding by default, but it also supports binary inputs like what we've seen, the JPEG, and you can actually program it to support other binary inputs as well. And it also supports OpenAPI, if you're familiar with that. It basically allows auto-generating client code with basically virtually every programming language you can think of automatically for the server. So that's a pretty cool feature. Containers. So containers are very useful tooling for doing lightweight virtualization, isolation, and it runs everywhere. So it's very useful. And we actually recommend that you run the model server for production settings. You will run model server in a container because it's extremely scalable. And this is how this workflow will look like. We have an MMS Docker image that is available on Docker Hub that you can just pull, or you can also build it locally because we have the Docker file available also in the MMS repository. And this basically builds this container, which we've created for you, which is built for scalability. So it includes stuff like this container includes Nginx as a reverse proxy for handling load properly. It includes MXNet, and then the MXNet model server on top of these two. You can run this container on your container orchestration platform of choice. You can run it with Kubernetes, you can run it with Amazon ECS, or with Docker. And the important thing is, once you put a load balancer in front of it, you can have multiple containers running, and this is really the story that allows you to scale out your service as your load increases. So just advantages of using the model server container images. It's production ready. It comes with everything I mentioned, and it's ready for scale. It's robust, and the scalable setup actually also takes care of leveraging all of the CPUs and GPUs you have available. And scaling out is easy, and I think that's the important story here with this container solution for the model serving. As your load increases, it's very easy to just throw more containers behind the load balancer and scale out this way. And as I said, the pre-configured images are available on Docker Hub. You can just pull it from there, and there's also a nice README there explaining how you would use it. Operational metrics. I mentioned the need for monitoring as something that is super critical when you run a production service. And model server actually supports these metrics out of the box. It supports metrics for things like requests, latencies, resource utilization for CPU, disk, memory. It supports two dimensions, the model name and the host name, because sometimes you'll have the same model deployed on multiple hosts and you want to aggregate these metrics. But sometimes you also want to be able to look at different models just in one single host. So these two dimensions are reported, and they allow you to slice and dice the metrics as you see fit. The target is either log file or CSV, but it also has built-in integration with AWS CloudWatch, which makes it extremely easy to set up a dashboard like that. It's like, 1 minute thing. This is an example of a dashboard when we ran some load tests. So you can see the resource utilization on the upper left corner. Below that, inference latencies. You can see the P50 and the P95. The number of incoming prediction requests, the pre-process latency, so just this phase of handling requests that is about your custom pre-processed code is also captured, and lots of other metrics. And that's an extremely useful feature for anyone who is running a production service. And lastly, Onyx Support. So with a show of hand, who has heard of Onyx? Okay, so very few of you. I will briefly go through that because I don't have a lot of time. But Onyx tries to solve the problem of the fact that there's many frameworks in deep learning, there's many platforms, and it's very hard to actually move between frameworks and move between platforms. And Onyx tries to solve that. Onyx is a common definition of neural networks. Amazon created it together with Microsoft and Facebook in collaboration, and it's now gaining momentum. More and more vendors are ramping up on that. And Onyx is the format that allows you to move between frameworks and platform. And just to give you an example, I can train my neural network with PyTorch, export it to Onyx, and then load this Onyx file in MXNet for inference at scale. Or I can take my MXNet trained model, export it to Onyx, and then run it on an iOS device with Core ML. So that's extremely powerful idea that is also pretty simple. MMS supports Onyx. You can, just like you can give MMS an MXNet model, you can give it an Onyx model, and it will serve it. And yeah, that feature is available today. So that's one important feature of the model server. I want to quickly talk about MMS 1.0. The current version of MMS is 0.4, and we're going to release version 1.0 really soon. As I said, it's an open source project. It's very easy for anyone to just benefit from it. But the big things on version 1.0 is, first of all, we completely re-architected the server. The user experience is largely the same, but the architecture is significantly more scalable. And so we get actually really, really better performance. Latency is 7x lower compared to the previous version, and scalability is 10x higher, which is a huge improvement. And we also have a new control plane API. So based on feedback we got inside of Amazon for the model server, we learned that actually users want the ability to use an API to tell the server to load models, to unload old models, and to scale how many workers we have for every model. And that capability is now available, and it's extremely useful. It really supports the story around availability, because now if you want to deploy new models, you don't need to take the server down. You can just call a control plane API, asking to load new models or unload existing models. So that's going to come out very, very soon, so stay tuned. I want to also encourage you to evaluate Apache MXNet. This slide has some details on how you can evaluate it, the MXNet and the model server, and we actually have a team that can support you if you're considering to use MXNet for your deep learning work. So you can reach out to mxnet-info@amazon.com, or you can talk to me as well after this talk. And I'm out of time. So I hope you enjoyed the talk. I really recommend you to try out the model server. It's open source. You just use it, file an issue, contribute code. And if you're interested in joining the beta for the 1.0 version, you can just come by and talk to me. Okay. Any questions? Okay. Thank you.